As founder of the Smart Structures and Dynamics Lab, I welcome you all to this introductory presentation. We started this lab in the year 2009 to create awareness about smart structures and dynamics field. Smart materials, they are perhaps the most fascinating materials which were developed in the 20th century. Now, they are called smart because they possess responsive capabilities to stimuli. We apply a certain stimulus and we see some kind of response. The materials, they change their physical properties when we apply certain kind of stimuli. Now, the main smart material which we are focusing in the virtual smart structures and dynamics lab is the piezo material. Now, piezoelectric material, the word piezoelectricity comes from two words, piezo meaning pressure and the second word is electricity. Now, this looks like any other ordinary material. Here we have some kinds of piezo materials of different shapes and sizes. It is in the form of a sheet. Now, why it is called smart? Because if we apply an electric field across the terminus of the patch tends to undergo change in its size, and conversely if we apply stress to the piezo material, what we find is we find the development of charges. So, these dual relations, both direct and converse effects, they are exhibited by the piezo material. Now, what is a smart structure? Here a smart structure is basically a system which has built in sensors and or actuators, and it might also have a control mechanism by which it is also capable of sensing a stimulus and responding to the same. Now, if we bond the same piezo material on a structure such as this one, now the structure becomes smart. The smart material, it provides signal. By this signal we can identify the dynamic characteristics of the structure. So, this is the point we tend to use in the smart structures and dynamics lab. So, here the main instrumentation or the sensors which we are using, they are basically piezo sensors. So, our lab, the virtual smart structures and dynamics lab, it provides a platform to the inquisitive students. They can be B.Tech students, they can be postgraduate students, they can be research scholars, or they can even be high school students, so that they can perform basic experiments related to smart structures in an online fashion. So, the colleges do not have to invest money in instrumentation or the sensors. Now, this is a highly interdisciplinary lab. So, we invite students from all disciplines to perform experiments and learn the basic concepts of smart materials and structures. Through this lab, we aim to make the teaching and learning exercise a fun activity. We have experiments of diverse nature. For B.Tech students, we have very preliminary experiments, simulation based, related to structural dynamics. For higher master students, we have more rigorous experiments, and similarly for research scholars, we have lot of additional online resources. So, what we expect is that the student reads the manual, understands, and then he performs the experiment. However, if you are high school student and somehow if you are not able to understand the manual in the first attempt, do not get disheartened. Continue and perform the experiment. Discuss the things with your teachers, and when you repeat the process few times, you will definitely understand it. Please feel free to contact us. So, this provides you a platform where you can learn concepts at your own pace, and do not be afraid to commit mistakes, because it is for your own learning. So, if you do mistakes, by your mistakes also you can learn. So, here we are planning this introductory session by two eminent team members of our lab, Naveed and Sushmita. They will brief you about the various experiments which are to be conducted and how these are to be conducted. Naveed is the senior most research scholar in our lab, and she has been active in the area of energy harvesting and smart materials for over 3 years. Sushmita has just completed her MTech and she is working in the area of electromechanical impedance technique. So, this whole orientation is designed so that you do not face any problem when you do experiments. So, with this I wish that you will enjoy the orientation part and then after this you will be in position to do the experiments. Thank you very much.
Hello everybody, I am Naveed Kaur. I am a research scholar at Indian Institute of Technology, IIT Delhi. I am working under the supervision of Dr. Suresh Bhalla. My research work is the feasibility of integrated structural health monitoring and energy harvesting using piezo sensors. Today I will be delivering a talk on virtual smart structures and dynamics lab at IIT Delhi. I have divided my whole lecture in 3 parts. First, I will be delivering introductory lecture on the smart materials. Then I will be covering the introduction about the virtual smart structures and dynamics lab and I will take you to the tour of the lab. And next I will be covering the steps to perform the experiment. This is also divided into 2 parts. First is I will be briefing you the steps to perform the experiment offline, then I will be conducting the experiments online. So, starting with the introductory lecture. Now, first is what is a smart material? Which property of any material compels it to behave smartly? So, any material which has the ability to change its physical properties in a specific manner when a specific type of input is applied on them is a smart material. So, different type of smart materials are piezoelectric materials, electrorheological fluids, shape memory alloys, optical fibers. So, now taking them one by one, first is the piezoelectric material. So, in these materials when stress is applied they produce electrical charges and when electrical field is applied on these materials they produce mechanical strain. So, when electrical field is applied on them they will either get contracted or maybe expanded. This will be clear when we will watch this video. So, in this video you can see the material is getting deformed, it is getting compressed when voltage is applied on them. Next are the shape memory alloys. These materials have a unique property that they memorize their shape. So, when heat is given, when these materials are heated, they memorize their original shape. They regain their original shape when they are heated. So, let us watch this video to understand.
So in the previous video, I showed how the nitinol remembers its original form when it's heated up. Now, many people were wondering if you could tie it in a knot and would it revert to its original shape? Let's give that a go. So I tried a
In this bowl they have just put hot water and this is a wire made of shape memory alloy and when he will put this wire in the hot water it will regain its original shape.
This array of different knots and from what I've noticed it kind of works. Even though I couldn't get the knot as tight as I wanted because it's made from metal, it's still pretty impressive. Okay, let's try something else. So here's a new batch of nitinol which has some more wire around the top of a can and heated it to...
Now he is trying to give a shape of circular shape to this wire. He will heat this wire at 500 degrees Celsius to make it to memorize this circular shape by revolving the wire around this cane.
Set the circular shape. And now when I heat up this pathetic excuse for a triangle, it reverts back to a circular shape. Interesting. Now for this last test, it's just a bit of fun. I scrumpled up a big bunch of straight nitinol and threw it in a jar of hot water, just to see what would happen really. Here we go. And it kind of looks like a spider's web. So there we have it. More experiments with nitinol.
Right. Next type is the electrorheological fluids. On these materials, when electrical field is applied, they change their viscosity. Let us watch this video. So, when electrical field is not applied across these electrodes, the fluid is just flowing as. And now they have applied the electrical field. Now you can see the change in the viscosity of the fluid. It has got thicker. And again he removes the, as he removes the field, the liquid then again starts flowing. Next type is the optical fibers. So, when there is a change in temperature or pressure and when mechanical strains are applied on these type of materials, there is a change in the optoelectronic signals for the optical fibers. And the other type is the magnetostrictive materials. So, when magnetic field is applied on these type of materials, they produce mechanical strains. Sorry. Now, we will be concentrating on the piezoelectric materials because the whole lab is actually based on these piezoelectric materials. In these material, in the direct effect, they show two different type of effects. In the direct effect, when mechanical stresses are applied on these materials, they produce electrical charges. So, in this animation, you can see when the material, piezoelectric material is compressed, voltage in the form of positive negative you can see is being produced in these materials. The other effect is the converse effect. So, in this effect when the electrical field is applied on piezoelectric materials, they produce mechanical strain. So, in this figure you can see when electrical field is applied across these this piezoelectric material, it is getting elongated. Next are the constitutive relations. So, for any elastic material, when strain is applied, it produces stress, but in the piezoelectric material, in addition to stress, electric field is also being generated. And for any elastic material, when there is a change in the charge density, electrical field is produced, but in piezoelectric materials, in addition to electrical field, there is a development of stress. This equation is used for the sensor application. When the piezoelectric material is used as a sensor, then this equation is used, and when E3 is 0, when there is no electrical field, so only stresses are being produced, then the equation will reduce to this, and so it becomes 0, this E3 becomes 0. So, using the basic relation, the voltage generated by the piezoelectric material is given by this relation in the direct effect. So, voltage is actually directly proportional to the strain. This equation is for the direct effect when the piezoelectric material is used as a sensor. And the sensitivity of piezo material is 200 millivolts micrometer per meter. This is the plot of a typical voltage response of a piezoelectric material attached to the structure. In this material, in this plot you can see the variation of voltage with respect to time, and you can observe that initially the voltage is high and slowly it dies down due to damping of the material. Next, we have done the FFT of that same voltage response and converted that time domain data into frequency domain. So, the advantage of performing FFT is that we will get the frequency content of any response. So, what is the advantage of getting frequency content is that we will come to know which frequency is contributing maximum to the response of the structure, and that frequency is actually the natural frequency of that structure. So, possible application of piezo materials are: in the direct effect, it can be used as a sensor which is used for the structural health monitoring of any structure, that is SHM. In the converse effect, piezo sensors can be used as actuators, and when these materials are used in a combined action, that is direct and the converse effect simultaneously, they are used as electromechanical impedance transducers. This technique of SHM is called EMI, electromechanical impedance technique. In the direct effect, the frequency range is low, it is in the range of hertz. So, 5 hertz to 100 hertz, and the EMI technique is a high frequency technique in which the frequency becomes 30 kilohertz to 400 kilohertz. So, the frequency range has now changed from hertz to kilohertz in the EMI technique. So, in EMI technique, a PZT patch is surface bonded to the structure using adhesive and excited at a frequency ranging between 30 to 400 kilohertz using an impedance analyzer. You can see a PZT patch is being attached to this host structure, and what is being done in this EMI technique is that we choose a subset of frequencies from this range, and for the first frequency, for F1 frequency, among that subset, a sine wave signal is generated by the LCR meter and then transferred to this PZT patch. In this first stage of EMI technique, this PZT patch will act as an actuator. So, as this PZT patch is attached to the host structure, so it will cause the host structure to actuate, to vibrate. So, in this second stage of EMI technique, this same PZT patch will start acting as a sensor. Now, it will start sensing the response of this structure, and it will acquire the data using the LCR meter in the form of admittance, and that is real being conductance and the susceptance being the imaginary part. So, in EMI technique, the PZT patch acts as a sensor and an actuator simultaneously. So, in this diagram you can see a PZT patch being attached to the structure, and using the LCR meter which is connected to the computer, the signature for this whole range which we have chosen for the EMI technique is being acquired. These are the conductance and the susceptance plot of typical signature, and these plots are like in LCR meter captures the conductance values for each frequency and keeps on adding, and this becomes the conductance signature of the PZT patch for any attached to any structure. Now, we have considered a I section in which we have given a damage at the bottom flange. We have created a hole of 5 mm dia, and when we compare the signatures, this is the undamaged signature, conductance signature of the PZT patch, and when the damaged signature is captured, you can see there is a clear difference between the undamaged and the damaged signature. So, in this way we can clearly identify the damage in any structure using the EMI technique. Next part is the introduction of the virtual smart structures and dynamics lab, and I will take you to the tour of this lab. This is the whole virtual smart structures and dynamics lab at IIT Delhi. It is a part of the virtual lab project sponsored by MHRD. It has also been selected as one of the virtual labs under the pilot project of QEEE, Quality Enhancement and Engineering Education. So, you can see all the experimental setup for the experiments which are performed in this lab. I will be explaining all of them in my further slides. So, in this lab there are total 8 experiments. 4 are the trigger based experiment. Experiment number 1 to 4 are trigger based experiments, and experiment number 5 to 8 are simulation based experiment. Trigger based experiments, the user actually triggers the experimental setup and he acquires the data and saves the data in his computer. So, the user gets the real life feeling of performing the experiment in a real life. So, also the video and audio links which are available on the website, they gives the user a feeling of performing the experiment in real life. And in the simulation based experiment, the idea is to use the computer models. So, in order to understand the basic concepts which are of the dynamics, these experiments have been fabricated. So, you can see the students performing the experiments remotely. Next is the VSSDL tour. First experiment is based on the vibration characteristics of this cantilever beam. The aim of this experiment is to get the natural frequency of this cantilever beam when it is excited under free vibrations. The PZT patch is attached at the fixed end and the beam is excited by this revolving wheel. So, it helps to create a constant load at constant time intervals. This is the mic which is used to create the audio effects. When we will perform this experiment, we will come to know the voice being generated by this hammer hitting. And this is the camera which enables you to see the whole setup for experiment 1 and 4. The readings are captured using this digital multimeter DMM. This DMM is actually connected to the user's computer remotely via internet using the software called vPro. The vPro is a mandate to perform trigger based experiments in this lab. So, the links for this software is available on the website. So, whatever readings are being captured by this instrument DMM, they are transferred to the user's computer via vPro software remotely through internet. Next experiment is the aim of the next experiment 2 is to get the axial modes of a freely suspended aluminum bar. In real life, it is very difficult to achieve the higher order modes. So, this experiment enables us to get the higher order modes of any structure which is a aluminum bar in this case. So, you can see a bar which is suspended freely with the help of this flexible tape. In this bar, a PZT patch is attached here. In this experiment, actually 2 PZT patches are attached, one at the top and the other at the back side, and these PZT patches are connected in parallel in order to get the axial mode of this aluminum bar. The readings for this experiment are being captured by LCR meter. This is the instrument which is used for capturing the data. This instrument is called LCR, and this is used for the experiments which are based on EMI technique. It captures the conductance and the susceptance signatures of the PZT patch, and this LCR meter is also connected to the user's computer via internet through vPro software. So, in this experiment also you need vPro software to perform the experiment. Next is the experiment number 3. This experiment is based on forced vibrations. So, the aim of this experiment is to get the natural frequency of this 3.2 meter long steel beam under the forced vibration. The difference between experiment number 1 and 3 is that the first experiment was based on the free vibrations. So, however, in the experiment number 3 it is based on the forced vibrations which are produced by this shaker. So, the modes which are missed in the first experiment can be deliberately captured using this shaker, which can be adjusted for any frequency range for excitation. So, you can see the 3.2 meter long steel beam closely in this video. The shaker is kept at the bottom and it is attached to the bottom flange of the beam. The stringer of this shaker is attached to the bottom flange of the beam. This camera is used for capturing the video for experiment number 3. This is the function generator which will produce the electrical signal in the form of sine wave, and we have adjusted the sine wave frequency in a sweep form using this function generator. This electrical signal is transferred to this amplifier which amplifies this signal and then finally transfers that signal to the shaker. So, shaker then converts that electrical signal to the mechanical signal in the form of force. Next is experiment number 4. This experiment is based on photogrammetry. So, the aim of this experiment is to plot a load versus deflection graph when different loads are being kept on this simply supported beam. The deflection of this point C is measured using this using the photogrammetry. So, the whole experimental setup, the picture of this setup is captured via the camera. We know the distance between the point A and B, it is 100 mm, and we draw normal from point C to line AB. As we know the distance between these 2 points, so we can get the length of this line AB and we can calibrate the length from this point C to line AB. Next step is, in the next step we put the load on this beam. So, first is the no weight condition, in which there is no weight on the on this beam and we capture the picture and measure the length of line AC. And in the second step we put a load, first load on this simply supported beam and it will get deflected, and we will then again measure the length of the line C to line AB, and similarly we will repeat this process for different load values. So, we will keep on adding the load on this beam and we will get the the length of this line and calibrate the length with this reference line AB. This will be more clear when we will perform the experiment. Next stage is to perform the experiment. So, now I will be covering the steps to perform experiment in the lab. First I will be covering the steps which are offline, then in the second stage I will be performing the experiments online. So, when we click this link ssdl.iitd.ac.in vssdl home. So, you will be prompted to this page. As I have told that there are 8 experiment, 4 trigger based experiments and next 4 simulation based experiments. So, you can see the list of these experiments here. On the home page we have given the links of the videos which helps you to understand the theory behind the experiments. So, these links are can be easily accessible for better understanding of the experiments, and these videos are specifically based on the experiments being performed in the VSSDL lab. Also there is a link for QEEE package. In this link we have given a very explanatory way to for the step by step procedure to perform the experiment for all the experiments. So, first taking the trigger based experiments. Experiment number 1, as I have already explained the experimentation, the instruments being used for experiment, and I have already explained the aim of this experiment, which is to get the vibrational characteristics of this aluminum cantilever. So, the very first thing which is expected from the users is that they read the manual of the experiment. Next step is to perform the pre-experimental quiz. For all the experiments we have given a pre-experimental and a post-experimental quiz link. So, before performing the experiment it is expected that the user performs this experimental quiz. Next thing, to perform the trigger based experiment the user require the vPro software. So, we have given the links to download the software on the website. So, the user can install the softwares from these links. Next he can see the real setup of the experiment by clicking this link, and then he can click this link to perform the experiment. So, when he has installed the vPro software and when he performs this experiment he will get this screen. In this the user first specifies the file name and he can give the path of the directory where he can store the data. Then he can give he needs to give the sampling interval. Here we will give the 1 millisecond and the number of readings 5000. So, when he clicks this button play, he will get these two graphs. First graph is for the voltage response with varying with time, and the second plot is the FFT plot. So, as I have told that FFT gives the frequency content of any voltage, any response. So, from this plot we can get the experimental natural frequency of the cantilever. So, you can see that just with a click we can get the natural frequency of a structure. The next the aim of this experiment is now to compare the natural frequency which can be obtained from this formula, which is available in the manual of this experiment, and compare it with this experimental natural frequency. So, after that now the user is expected to perform the post experimental quiz. Next is experiment number 2. In this experiment the aim is to identify the high frequency axial modes of this freely suspended beam. Again the user is expected to read the manual and perform the pre-experimental quiz. If he has already installed the vPro software, he does not need to install it again for the experiment number 2. And he can see the real setup of this experiment 2 by clicking this link. And when he clicks this link to perform the experiment, he will be prompted to this screen. Again he can give the path of this file name where the data will be stored. In this experiment, the user needs to give a frequency range of 100k to 120k with a step of interval of 100 hertz, and when he clicks this button play, these two graphs will come. This is the conductance plot varying with the frequency which we have chosen, and this is the susceptance plot. Again the aim of this experiment is to compare the natural frequency which we have got experimentally. So, this is the natural frequency corresponding conductance plot, and this is the theoretical formula to get the theoretical natural frequency. It is available in the manual. So, the aim is to compare the theoretical natural frequency with the experimental natural frequency. Then again after performing the experiment, the user needs to perform the post experimental quiz. In experiment number 3, the aim is to get the dynamic characteristics of this 3.2 meter long steel beam under forced excitation. So, it is a forced excitation based experiment. The user is again expected to read the manual and perform the pre-experimental quiz, and here using these links he can see the real time setup of the experiment, and with this click he needs to perform the experiment. And again he can give the file name here, and he can choose the directory where he wants to save the file. Sampling interval he can give 1 millisecond, number of readings 5000, and when he clicks this button play, he will get these two plots. First is the voltage response varying with time, and this is the FFT of this voltage response. So, the aim of this experiment is to compare this natural frequency with the theoretical frequency. In experiment number 4, it is based on the photogrammetry. So, when he will perform the experiment 4, he will be prompted to this window. The user then needs to capture this picture and save it for the first case when there is no weight on this beam. So, I will explain the steps to get the deflection for the case when there is no weight and when there is first weight. So, those steps are required to be repeated for all the different 4 loads which are being added simultaneously. So, in the first case when there is no weight, the user will save that picture and he needs to open that picture in Word, and the user is now required to draw a line between these points A and B in Word. As we know, the distance between these 2 points is actually 100 mm. So, he can relate the length which he has got in the Word with this 100 mm. So, we can say this 8.61 units is equivalent to 100 mm. Then he will draw a line from point C to line AB and he will measure the length of this line. Now, he can relate the length, this length with the equivalent length of 100 mm using this formula. So, we have designated this equivalent length to y1. Y1 corresponds to the length of this line from point C to point AB for no weight case. Similarly, he will capture the picture for the second case when there is one weight kept on the beam. Now, the beam is expected to deflect under this load and this length is expected to increase. The length between C and AB is expected to increase. So, again he will relate this length with the 100 mm length and get a equivalent length which we have designated as y2 for case 2. So, the deflection for the first case is when there is no weight and when first weight of 0.43 newtons is kept on the beam, that can be calculated by this formula delta y is equal to y2 minus y1. So, in this way when the second weight is kept, he will get the deflection and similarly he will needs to repeat these steps for all the weights. And finally, he needs to plot the load versus the deflection curve. Next are the simulation based experiments. There are like I already told, there are 4 different experiments which are based on simulation. I will be covering experiment number 7 and the 5, 6 and 8 experiments will be covered by Sushmita. So, this experiment number 7 is based on the damage detection and the qualitative quantification using the EMI technique. In this experiment, we have considered a 2D structure, a plate structure in which we will be acquiring the signature in the undamaged state, and for the damage we have created holes in this 2D plate structure. So, first the user will read the manual of this experiment and perform the quiz. So, first step is to acquire the signature for the pristine stage, that is the undamaged stage. When he clicks this link acquire signature, he will be prompted to this screen. Here the user needs to give the frequency range. So, the recommended range is 115 hertz to 134 hertz and he will click this button submit. So, the computer starts taking the data for the given range and this kind of plot will come. The user can download the data using this link and click this link next experiment to proceed further. The similar steps will be repeated for the damage condition. So, when he will press this button induce damage, 3 different type of damages will be given in this 2D structure. First is the incipient damage, second is the moderate damage and third is the severe damage. In the incipient damage, we have created 2 holes in this 2D plate structure, for the moderate 4 holes and for the severe we have created 6 holes. So, the steps which we have done for the pristine stage will be repeated again for the incipient level damage and then for the moderate level and severe damage. Now, when the user has got the data for all the 4 stages undamaged and the 3 damaged stages, he will compare he needs to compare the conductance plot, conductance signature for the pristine and the damaged stages, and also he needs to plot a histogram of the RMSD value, which can be the formula for this RMSD can be referred in the manual. So, again after performing the experiment, the user needs to perform the post experimental quiz. And now next step is to perform these experiments online. Now, continuing with the last part of the lecture, here we will be explaining you the steps of the experiments which are required to perform the experiments online. So, in this part the user will come to know the experiments, the steps from the user's point of view. Starting with experiment number 1. So, this is how the so this is the user interface starting with experiment number 1. So, as I have told that there is a link for the manual of experiment. So, here you can see all the steps are very briefly given in this manual. So, the user needs to read this manual, and this link, by clicking this link, another thing I like to add is that for viewing the real setup of this experiment, it is recommended that the user opens this link in the Internet Explorer. So, for experiment 1, when the user clicks this link, switch on the sound of this setup. So, you can see the real time setup of the experiment number 1. The username and password required to open this camera setting is guest, ID is guest and password is also guest. So, the user can increase the size of this page by changing the settings in the client settings. So, you can increase the size by changing the view size properties. So, you have to bear with it. So, the connecting time with the camera depends on the internet speed. I will reduce the size to the smaller size again to get the sound effects. So, now here in this you can see the hammer is continuously impacting the cantilever beam, and you can also hear the noise of the impact being produced by this hammer. Now, we will perform the experiment by clicking this link in experiment 1. So, now to perform the experiment, the user should be using the Chrome browser. So, when this exe file will be downloaded, so now when he using the file name, whatever he wants to give, he can give the file name here and change the directory path. When he clicks the button play, I have already given 1 millisecond sampling and the total number of readings 5000. So, when I click this button play, it again asks me the name and the path of the file. I will keep it same. So, you can see the impact of the hammer is producing voltage response in the PZT patch. Now, why we are getting two different responses here is that the hammer in the 5000 readings, during this 5 seconds, the hammer has hit the cantilever beam twice. That is why we are getting two impact responses, and this plot gives the FFT response of this voltage. So, when you zoom this part, you can see a very sharp peak at a frequency of 19 hertz. So, this 19 hertz is actually the natural frequency of that cantilever beam. So, this experimental natural frequency has to be compared with the theoretical frequency which I have explained in my presentation. Similarly, we will proceed for the experiment number 2. So, again the manual is given, you can read the instructions in this manual, and also the pre-experimental quiz and the post-experimental quiz is given here. The user needs to perform the pre and the post-experimental quiz for all the experiments before performing and after performing the experiment. So, again when he clicks this button, it has to be opened in Internet Explorer. Experiment 2. To see the real time setup, so password is guessed, ID and password is guessed and guessed. In this experiment you do not need to enable the sound for experiment 2. So, you can see the aluminum bar hanging in a free condition using this flexible tape. So, this is the real time setup for the experiment number 2. Again for experiment 2, as I have already explained the steps, if the user clicks this button, he will be prompted to this page. Here the frequency range 100K to 120K, file name he can give, also the file path he wants to, if he wants to change, he can change from here, and when he starts the experiment, it start capturing the conductance and the susceptance values in real time for experiment number 2. So, you will ultimately get the expected plot as I have shown in my presentation. So, I will stop it and proceed further for the next experiment. So, third experiment, as I have told that in this experiment is based on the forced excitation being produced by the shaker. So, in this experiment the forcing frequency which we are giving is a sine wave with a frequency ranging from 2 hertz to 48 hertz. So, that has been given by using the function generator. So, to see the real time setup of this experiment, we will open the website in Internet Explorer, open the experiment number 3, click here to see the experiment, guessed, password, OK. So, this connecting time with the camera depends upon the speed of your internet connection. So, to perform the experiment, it has to be done in Chrome, and to see this setup, it has to be opened in Internet Explorer. So, for experiment 3, I will switch on the sound so that you can get the real time feeling of performing the experiment. Okay. So, here you can see the shaker, it is connected to the bottom flange of the beam. The snoring sound which you are hearing is being produced by this shaker, as we have given a sweep frequency. So, between 2 hertz to 48 hertz, the natural frequency of this beam is lying. So, the natural frequency of this beam is around 40 hertz. So, when that frequency matches with the forced frequency produced by the shaker, maximum noise is being created. So, this snoring sound is produced by the resonance being produced due to the resonance when forcing frequency is matched with the natural frequency of this beam. Okay. Now, I will perform the experiment 3. It has to be performed in Chrome. So, it will download the VXC file. When I open that VXC file, again I have given 1 millisecond interval, 5000 readings. We can change the file name and the path. I will keep it as it is and start the experiment. It takes some time to capture 5000 readings. It is again asking me the location and the file name. This experiment also helps to get the natural frequency of the beam. So, as you can see the voltage response for 5 seconds, and this plot is the FFT of this voltage response. Now, when you see it closely, you can see the natural frequency of this beam is coming around 40 hertz, as we have given the frequency from 2 hertz to 48 hertz. So, now we can with a click get the natural frequency of that beam. Now, coming to experiment number 4, as I have explained that this experiment is based on the photogrammetry. So, I will open the setup camera in Explorer. Experiment 4, give the username as guest, password as a guest. Now, this is the setup for experiment 4. This consists of a simply supported beam. The camera for experiment 1 and 4 are same. So, you are also able to see experiment 1 here, but in this experiment we are bothered about the picture of experiment number 4. So, the user will click here to save the snapshot of this camera. He will click here, he can save this picture on say desktop. I will save it. So, in this way the user can save the picture wherever he wants to save, and the method of performing the experiment I have explained in the presentation. The user needs to draw a line between these 2 points A B, and he can calibrate the length of this line with line from point C to line A B. So, in this way he will perform, he will repeat the experiment for 4 different cases, and he will get the load versus deflection curve. And now experiment number 7, among the simulation based experiments, I will explain experiment number 7. So, in this case we have considered a 2D plate, and this experiment is based on the EMI technique. So, for the capturing the signature in the pristine stage, I will click this button, acquire signature. I will give a frequency range of 115 to 134 hertz and submit. The computer starts acquiring the data. This is actually the measured data for a plate structure. The user, after when the complete signature has been acquired, the user needs to click this button, download data. It takes some time to take readings. Now, when the computer has acquired the data, the user will click this button, download data. He can save this file anywhere he wants to save. He can choose the path and click this button, next experiment. And next step, he will induce the damage. As I have explained, there are 3 different type of damages. So, again he will repeat the data acquisition as we have done for the pristine stage. He will click this button, acquire signature for the incipient, moderate and the severe damage, and he needs to compare the signatures for the undamaged, that is pristine stage, with the 3 level of damages. So, he has got the Excel sheet in which there is a data for the undamaged stage and the 3 different damages. He will compare those data with each other, and he needs to plot a RMSD graph as explained in the manual of this experiment. So, next part will be covered by Sushmita, where she will be explaining the simulation based other 3 experiments, that is experiment number 5, 6 and 8, and further next experimental part she will be explaining.
Hello everyone, I am Sushmita. I completed my MTech from Indian Institute of Technology under supervision of Dr. Suresh Bhalla, and now I am working as a project assistant with him on the virtual smart structure and dynamics lab. Now I will quickly describe about the experiments of simulation based, that is experiment number 5, 6 and 8. The simulation based experiments are mainly for the beginners who are new in this field, and now I will quickly give a brief description of the simulation based experiment. During this experiment or before performing that, each of you can go through the pre and post experimental quiz, and which has been given with the link for each of the experiment. Now for the experiment number 5, a structure undergoes for free vibration when distributed from the static equilibrium position without any external dynamic excitation. So the structure vibrates at its natural frequency, which is the function of its stiffness, and its vibrating motion decays depending upon the damping ratio of the material. For this case, the simply supported beam was excited into a flexural mode, which resulted in altering compressive and tensile strain at the top and bottom faces simultaneously. The main objective of this experiment is to study the modes of the vibration for the simply supported beam under flexure. And the total model is based on the discrete system, where the user can easily get the natural frequency of the beam and simulate the first few modes shapes. Now, if we will go through the manual, then we can see that the natural frequency has been given by the formula, that is Fn equal to pi n square by 2 twice L square to by Ei by rho I, and the mode shape has been given by Yx equals to sin n pi x by L, where L is the length of the beam, Ei is the flexural rigidity, A cross sectional area, rho is the density, and Fn, which I already told, is the natural frequency. So now if we will look into the experiment, and if we are going to take a steel beam, then if we are going to perform that, then we are taking the length of the beam as a 10 meter, and the breadth is 3 meter, and the depth of the beam is 4 meter. And then if we will enter the density in kg per meter cube, then it is like 8050, and the Young's modulus will be 180 for stainless steel. And now the value for the value of n, if you are going to take the n equals to 1, then it will calculate the natural frequency. And here we can see the mode shapes in the animation form, and this is the another exercise for the users which they can perform after the experiment, where they have to plot the different values of L, and they can get the value of F for different values of L. Now for the experiment 6. The main objective of this experiment is to study the modes of the vibration for square plate, which is simply supported on all the edges using modal analysis. Modal analysis is a process whereby the structure is described in terms of natural dynamic characteristics as natural frequency, damping, and mode shapes. Now, if we will see this is also a discrete stiffness, where the stiffness and the mass damping will be modeled as a discrete property. Unlike a discrete system which possesses a finite number of degrees of freedom, the distributed system, which are considered to be the composed of the infinite number of infinitesimal mass particles, theoretically possess infinite number of degrees of freedom too. For this experiment, the plate has been divided into a number of strips along x and y axis. So, however, the first few modes are much significant, so it is not necessary to compute all of the modes. Hence, again, if we will go to the manual, then we can see that the natural frequency has been given by the Fn equals to pi m square plus n square by twice L square to d by rho t, where we can get the different modes of vibration for simply supported plate from the x and y direction both. And d is the parameter which has been given by Et cube by 12 into 1 minus v square. Now in this experiment, if we will take a concrete beam, and then the value of L is given by 10 meter, and the thickness is like 3 meter, and Poisson ratio for the concrete we are taking 0.2, and density is 2.2400, and E is 7 into 10 to the power 9. Then if you are taking the value of m equals to 1 and n equals to 1, then it will calculate the value of frequency, that is 73.990, and here it is, this animation is showing the mode shapes, and then and in addition there is also an exercise for the user at the end of the experiment, where the user can perform the experiment and needs to plot the graph between the frequency and length of the beam, and also for the previous case also plate, keeping all the other factors constant. Now if we will go to the next experiment, that is experiment number 8, where we will discuss about the Bandra ceiling bridge. Bandra ceiling bridge is basically a cable stayed bridge with a pre-stressed concrete viaduct on either side that links with the Bandra and Worli, and also the bridge was designed on the first cable stayed bridge to the constructed in open seas in India. And this bridge mainly having 3 parts. First one is the northern approach, where the structure is mainly made of present precast segmental construction, and for the part 2 it consists of the cable stayed Bandra bridge, and for part 3 it is made of south and approach structure mainly with precast segmental construction. As we already discussed earlier, it is not necessary to compute all the modes of only few modes are only significant. So, for this experiment also we are only interested to compute fewer mode. And if we will see for the first mode, the main aim of the experiment is to illustrate the fundamental modes of this beam of this bridge, and this is the first mode where we can see that the frequency is coming at 1.204. And if we will see the fourth mode, where the frequency is coming at 1.388 hertz, and for the 10th one, here we are only considering the 10 modes, then it is coming at 4.579. So, basically we are the main simulation study covered in our experiment is mainly based on the geometrical and material property of this bridge. The finite element model is highly idealized and not updated on the actual bridge model. So, the structural dynamic aspects covered are the idealized and may not be needed for the main construction of this bridge. This was the brief description of performing the experiments for our smart structure and dynamics lab, and hope this is going to be very useful for all of you, and wish you all a very happy experimentation. Thank you.
So, I hope you had a very good time with the introductory session of the virtual smart structures and dynamics lab. So, when you are doing the things for the first time, you need to install certain software, and this could be a little bit tedious process. So, do not get disheartened by this is only one time activity. So, you download the software, install as per the instructions, and then you perform the experiments as have been explained by Naveed and Sushmita. If you face any kind of problem, please contact us. Our endeavor is to make the things as user friendly as possible. So, please invite your friends also if you understand any experiment, and if you are very confident about it, to teach it to your next and best friend. By this way, you can help us in disseminating the knowledge and also in making the concept of smart materials and structures popular. We endeavor that more and more students, they will come forward and they will take up a research career in the field of smart materials and structures. So, please email your feedback to us. Thank you very much.